Morning everyone, we are Group 3 here to present about Chapters 17 and 18. Chapter 17, Sheet Forming Process. Sheet metal process generally involves plane stress loading and lower forces than bulk forming. Almost all sheet metal forming is considered as secondary processing. Shearing, bending, and drawing are the three main categories of sheet metal forming. Shearing has two stages: deformation and fracture. Fracture and tearing begins at the weakest point and progressively proceeds to the next weakest point. Punch and die must have a proper clearance. A simple type of shearing operation, as illustrated in pictures, goes this way. As the punch or upper blade pushes down the workpiece, the metal responds by flowing plastically into the die. Because the clearance between the two tools is small, usually between 5 to 20% of the thickness of the metal being cut, the deformation occurs as highly localized shear. As the punch pushes downward, the metal and the material flows into the die, with the opposite surface bulging slightly. An instability arises when the penetration is between 50 and 60% of the metal thickness. The actual amount depending on the strength and ductility of the material. The applied stress exceeds the shear strength, and the remaining material and the metal tears or ruptures through the rest of its thickness, linking the cutting edges of the punch and the die to produce an inwardly inclined fracture and a ragged edge or burr. After simple blanking is fine blanking. In fine blanking, there is lower support while the punch pushes down, and the lower support lowers itself as the punch pushes down, hence a cleaner cut of the material. Next is slitting. In slitting, sheets of metal, usually narrow ones, are being cut into narrower sheets. In piercing and blanking, are shearing operations where a part is removed from sheet material by forcing a shaped punch through the sheet and into the shaped die. The term piercing can also be used to describe the formation of a hole by a pointed punch where no metal is removed from the sheet, like driving a nail through the sheet metal. Lancing, on the other hand, can be combined with bending to form tabs or openings like those found in vents or louvers, as seen in the picture. Perforating consists of producing large numbers of closely spaced holes where a slug is removed from each hole. And notching is used to remove segments from along the edge of an existing product. In nibbling, a contour is progressively cut by producing a series of overlapping slits or notches. Shaving is a finishing operation in which a small amount of metal is sheared away from the edge of an already blank part. Cut-off. In cut-off, a punch and die are used to separate a stamping, or the product, from a strip of stock. The contour of the cut-off frequently completes the periphery of the workpiece. Cut-off operations are quite common in progressive die sequences, like several to be presented shortly. Dinking is a modified shearing operation that is used to blank shapes from low-strength materials such as rubber, fiber, and cloth. Here is a table of classification of the non-squeezing metal forming processes. There are three tools and dies for piercing and blanking. They are punch, die, and stripper plate, as seen in the image. Punches and dies must be aligned properly to ensure uniform clearance. The max cutting force can be determined by getting the perimeter length multiplied with the thickness multiplied to the material shear stress. Tilting the punch face angle can make the force needed to be reduced. It is also known as shear or rake angle. The periphery is cut in progressive fashion instead of simultaneously, thus reducing the needed force, just like scissors cutting through a can, as also seen in the image. Separate punch and holder set. These are also known as independent die sets. Holder and shoe are permanently aligned and guided by two or more guide pins. This reduces the production and time lost. Self-contained die sets, on the other hand, has only one ram pushes the punch downward. Springs pushes the rams upward, much similar to signature stamps. Punches and dies are usually made from low distortion and high and air hardenable tool steels, hardenable after machining, and minimal warpage. Die, prof- Die profile depth maintained at 3 mm to reduce friction and part of the die, thus allowing piece to fall freely after shearing. Dies single piece or component assembled are easier to produce, enables replacement of single section, can have components be removed and used for constructing other uh, con- can be used for constructing and tooling for other products. If periphery are simple lines, materials cut are soft metal or materials. These This process uses steel rule dies. Progressive die sets. Basically, it consists of two or more sets of punches and dies mounted in tandem. Strip stock is fed into the first die, where a hole is pierced and the ram descends. When the ram raises, the stock advances and the pierced hole is positioned under the blanking punch. Upon second descent, a pilot on the bottom of the blanking punch enters the hole that was pierced on the previous stroke to ensure accurate alignment. Further descent of the punch blanks the completed washer from the strip, and at the same time, the first punch pierces the hole for the next washer. As the process continues, a finished part is completed with each stroke of the press. Transfer dies. These dies are where individual parts are moved manually from operation to operation in a single press. In compound dies, on the other hand, piercing and blanking, or other combinations of operations occur sequentially during a single stroke of the ram. Dies of this type are usually more expensive to construct and are more susceptible to breakage. A Tourette-type punch press may be used when manufacturing many hosts of varying sizes and shapes and sheet components. Here is Here are some reminders for design and piercing. For design for piercing and blanking. Now let's proceed to bending. Bending is a plastic deformation of metals about a linear axis with little or no change in the surface area. Multiple bends can be made simultaneously, but not but to be classified as true bending. Simple bending, the metal outside is stretched and the metal inside is compressed. Neither stressed or compressed location is called a neutral axis, located between 1/3 to 1/2 from inner surface. In linear bends, thinning is greatest at the center, as can be seen in the picture. Inside thickening, inner side thickening, and outer side thinning. This kind This happening kind of offsets but moves free edges outward and results to distortion. Elastic recovery. It happens when the load is removed. Stretched region contracts and compressed region expands. This is also called as unbending or springback. The metal must be overbent by amount equal to subsequent springback. Springback amount factors are the type of material and the material thickness. Springback for softer material is 0.5 degree, for steels is 1 degree, and for stainless steel is 3 degrees. Springback amount increases as material strength increases. For the design for bending, you have to determine the smallest bend radius or the minimum bend radius formed without cracking. The pendant or ductility and toughness of material is also considered. A sharper bend, hence a larger springback. The bend radius must be greater than 4 times the material thickness and must provide springback compensation. Bends should be made with bend axis perpendicular to the rolling direction, just like seen in the picture. Metals bend tend to lengthen, and the lengthening is a function of the stock thickness and bend radius. The minimum length of protruding leg and bend is equal to the bend radius, added 1.5 thickness of the material. Air bend, bottoming, and coining dies. For bottoming, the contact and compress the full area within the tooling. The angle and the resulting bend is set by the geometry of the tooling, adjusted for subsequent springback, and the inside radius is that machined on the nose of the punch, while air bend dies produce the desired geometry by simple 3-point bending, because the resulting angle is controlled by the bottoming position of the upper die. A single set of tooling can produce a large range of bend geometries from 180 degrees through the included angle of the die. Coining, on the other hand, is a bottoming die continued to move beyond full contact position. Coining or bottoming with penetration is other name for coining. Springback can be significantly reduced, and more consistent results can be achieved with materials having variation in structure and thickness. Roll bending is a continuous form of 3-point bending where plates, sheets, beams, pipes, and even rolled shapes and extrusions are bent to a desired curvature using forming rolls. This is also available in wide ranges of sizes. Draw bending, compression bending, and press bending. In draw bending, a workpiece is clamped against a bending form and the entire assembly is rotated to draw the workpiece along a stationary pressure tool. In compression bending, bending form retains stationary and the pressure tool moves along the surface of the workpiece. In press bending, on the other hand, it utilizes a downward descending bend die which pushes into the center of a material that is supported on either side by wing dies. As the ram descends, the wing dies pivot up, bending the material around the form of the ram. Tube bending. The material bent is a tube or a pipe. The key parameters are the outside tube diameter, wall thickness, and the radius of the bend. A smaller diameter and a thick wall causes less problems. As the outside diameter increases, the wall thickness decreases, or the bend radius becomes smaller. The outside of the tube tends to pull to the center, flattening the tube, and the inside surface may wrinkle. For many years, a common method of overcoming this problem was to pack the tube with wet sand and produce the bend, and then remove the sand from the interior. Flexible mandrels have now replaced the sand and are currently available in wide variety of styles and sizes. Roll forming. This is a process involving the progressive bending of metal strip as it passes through a series of forming rolls at the speed of 80 meters per minute or 270 feet per minute. Only bending takes place, and all bends are parallel to one another. The thickness of the starting material is preserved except for the thinning of at the bend radii. By changing the rolls, a single roll forming machine can produce a wide variety of different shapes. However, changeover, setup, and adjustment may take several hours. Seaming and flanging. In seaming, bending operations can be used to to join the ends of sheet metal in some form of mechanical interlock, while in flanging, it involves a rolling operation on sheet metal in essentially the same manner as seams. In many cases, however, the forming of both flanges and seams is a drawing operation because the bending can occur along the curved axis. Straightening, flattening, or leveling. These are opposite operations of bending. Roll straightening or leveling subjects the material to a series of reverse bend. The rod, sheet, or wire is passed through a series of alternating upper and lower rolls with progressively decreased offsets. This configuration produces deep bends at the entry, decreasing to little or no bend at the exit. Structure leveling. Finite length sheets are gripped mechanically and stretched beyond the elastic limit to produce the desired flatness. Drawing and stretching processes. Drawing is when the starting material is a sheet. The drawing refers to a family of operations where plastic flow occurs over a curved axis, and the flat sheet is formed into a recessed, three-dimensional part with a depth more than several times the thickness of the metal. Spinning is a code-forming operation where a rotating disc of sheet metal is progressively shaped over a male form or mandrel to produce rotationally symmetrical shape, such as cones, hemispheres, cylinders, bells, and parabolas, as shown in the picture. A recent modification of metal spinning is laser-assisted metal spinning. A laser beam is focused directly ahead of the roller to heat and soften the material. Materials such as titanium, nickel-based alloys, and austenitic stainless steels can be spun with less difficulty, and the operation can be performed with less force and power. Cones, hemispheres, and similar shapes are often formed by shear forming or flow turning, a modification of the spinning process in which each element of the plank maintains its distance from the axis of rotation and the spinning flange remains vertical throughout the process. The roller provides highly localized pressure that plastically deforms and cold works the metal. Because there is no circumferential shrinkage, the metal flow is entirely by shear and no compensating stretch has to occur. Stretch forming, as illustrated in the picture, is an attractive means of producing large sheet metal parts in low or limited quantities. A sheet of metal is gripped by two or more sets of jaws that stretch it and wrap it around a single form block. Various combinations of stretching, wrapping, and block movements can be employed, depending on the shape of the part. The remaining parts of Chapter 17 and Chapter 18 will be discussed by Polo and Glenn, my groupmates.
I am Polo Elefante from 3IEA and I will be continuing the reporting on sheet forming process. I'm going to start with deep drawing and shallow drawing. Deep drawing is typically used to form solid bottom cylindrical or rectangular containers from sheet metal. The key variables for deep drawing are blank and punch diameter, punch and die radius, clearance, thickness of the blank, lubrication, and hold down pressure. The limitations of deep down drawing are wrinkling and tearing, but the different techniques that can be used to overcome these limitations are draw beads, vertical projections that match down grooves in the die and blank holder. Also, trimming may be used to reach the final dimensions. Forming with rubber tooling or fluid pressure. The process of this has been developed to seek and reduce tooling cost, decrease setup time and expense, extend the amount of deformation for a single set of tools. There are several alternatives for forming operations. Operations replace one of the dies with rubber or fluid pressure. This is called Guerin process. Other forming operations use fluid or rubber to transmit the pressure required to expand the blank metal. This is called bulging. Next is sheet hydroforming. Sheet hydroforming is a family of process in which a rubber bladder backed by fluid pressure replaces either the solid punch or the female die set. The advantages of sheet hydroforming is reduced cost of tooling, deeper parts can be formed without fracture, excellent surface finish, and accurate part dimensions. Tube hydroforming. Process for manufacturing strong, lightweight tubular components. It is a frequently used process for automotive industries. The advantages for tube hydroforming is that it is lightweight and high strength in materials. It designs with varying thickness or varying cross section. Wielded assemblies can be replaced by one-piece components. But the disadvantages for tube hydroforming is that it has a long cycle time and it is relatively high tooling, cost, and process setup. There are additional drawing operations. First, hot drawing. Second, high energy rate forming. Third, ironing. Fourth, embossing. And fifth, superplastic sheet forming. Hot drawing is when sheet metal has a large surface area and a small thickness, so it cools rapidly. Most sheet forming is done at mildly elevated temperature. For high energy rate forming, large amounts of energy in a very short time. Underwater explosions, underwater spark discharge, pneumatic mechanical means, internal combustion of gaseous mixtures, rapidly formed magnetic fields. For ironing, the process that thins the walls of a drawn cylinder by passing in between a punch and a die. For embossing, press working process in which raised lettering or other designs are impressed in sheet metal. For superplastic sheet forming, materials that can be elongated in the range of 2000 to 3000% can be used to form large, complex shaped parts. Superplastic forming techniques are similar to that of thermoplastics. Next, I will be discussing the properties of sheet material. Tensile strength of the material is important in determining which forming operations are appropriate. Sheet metal is often anistrophic, meaning the properties vary with direction or orientation. Majority of the failures during forming occur due to thinning or fracture. Strain analysis can be used to determine the best orientation for forming. Alternative methods of producing sheet-type products. There is electroforming and spray forming. Electroforming directly deposits metal onto pre-shaped forms or mandrels. Examples that can be used for electroforming are nickel, iron, copper, or silver. A wide variety of sizes and shapes can be made by electroforming. For spray forming, it uses powdered material in a plasma torch. Molten metal can also be sprayed. Pipe welding. A scalp is a long strip of steel used in welding. Under pipe welding is butt welded pipe and lap welded pipe. For butt welded pipe, the steel scalp is heated to a specific hot working temperature. The scalp rolls back on each other through rollers and produces a welded seam. For lap welded pipe, the scalp has beveled edges and the rolls form the weld by forcing the lapped edges down. Here you will see the various types of press drive mechanisms, like the crank, the eccentric, knuckle joint, toggle, screw, and the hydraulic. In this table, it will show the classification of presses according to the type of frame. There is arc, gap, and straight-sided. Under arc, there is crank or eccentric, and percussion. Under gap, there is foot, bench, vertical, inclinable, open back, horn, and turret. Under straight-sided, there are many variations, but all with straight-sided frames. Here are the examples of presses. For the first figure, it shows the arrangement of dies and the transfer mechanism used in the transfer presses. In the second figure, it shows that various operations can be performed during the production of stamped and drawn parts on the transfer press. In this last figure, it shows a multi-slide machine. It shows how the material enters from the right and progresses to the left as the operations are performed. For the summary of this part of the report, we can say that sheet forming process can be grouped in several broad categories: shearing, bending, drawing, and forming. We can also say that the basic sheet forming operations involve a press, punch or ram, and a set of dies. The last thing we can say is that material properties, geometry of the starting material, and the geometry of the desired final product play important roles in determining the best process. Thank you.
Hi everyone, I'm Glenn Gerald Castaneda and I will be reporting Chapter 18, Powder Metallurgy. Introduction. Powder metallurgy is the name given to the process by which fine powdered materials are blended, pressed into a desired shape, and then heated to bond surfaces. It is typically used when large amounts of small, intricate parts with high precisions are required. Little material waste and unusual mixtures can be utilized. It is also used for parts in the automotive industry, household appliances, and recreational equipment. There are four basic steps. First is powder manufacture. Second one is mixing or blending. Third one is compacting, and the fourth one is sintering. Powder manufacture. The properties of powder metallurgy products are highly dependent on the characteristic of starting powders. Some important properties and characteristics are chemistry and purity, particle size, size distribution, particle shape, surface texture. It is useful in producing pre-alloyed powders because each powder particle can have desired alloy composition. The majority of commercial powder is produced by some form of melt atomization. What is atomization? Atomization is a process where liquid metal is fragmented into small droplets that cool and solidify into particles. There are additional methods of powder manufactures. These methods are: first is the chemical reduction of particulate compounds. Second is electrolytic deposition. Third is pulverization or grinding. Fourth is thermal decomposition or particle hydrides. Fifth is precipitation from solution, and the last one is condensation of metal vapors. It is almost any metal or alloy can be converted into powder. Next is rapidly solidified powder or microcrystalline and amorphous. If the cooling rate of an atomized liquid is increased, ultrafine or microcrystalline size grain can form. Some metals can solidify without becoming crystalline. It is called amorphous materials. Amorphous materials can have high strength, improve corrosion resistance, and reduce energy to induce and reverse magnetization. In powder testing and evaluation, powder should be evaluated for their suitability for further processing. Flow rate measures the ease with which powder can be fed and distributed into a die. Apparent density is the measure of a powder's ability to fill available space without external pressure. Compressibility is the effectiveness of applied pressure. Grain strength is used to describe the strength of the pressed powder after compacting. Powder mixing and blending. The majority of powders are mixed with other powders, binders, and lubricants to achieve the desired characteristic in the finished product. Sufficient diffusion, must occur during sintering to ensure a uniform chemistry and structure. Unique composites can be produced. Blending or mixing operations can be done either wet or dry. In compacting, loose powder is compacted and densified into a shape known as green compact. Most compacting is done with mechanical presses and rigid tools. Hydraulic and pneumatic presses are also used. In Table 18.1, it is shown typical compaction pressures of various applications. Compaction sequence. Powders do not flow like liquid. They simply compress until an equal and opposing force is created. This opposing force is created from a combination of, first is the resistance by the bottom punch, and the second is the friction between the particles and die surface. In figure 18.4, typical compaction sequence for a single level part showing the function of the feed shoe, die cork rod, and upper and lower punches. In the figure, the loose powder is the shaded one and the compacted powder is the solid black. Additional considerations during compacting. When the pressure applied by one punch, the maximum density occurs right below the punch surface and decreases away from the punch. For in the figure 18.5, compaction with a single moving punch showing the resultant non-uniform density, it is the shaded one, and the highest where particle movement is the greatest. For complex shapes, multiple punches should be used. In figure 18.6, the density distribution obtained with this double acting press and two moving punches. Note that the increased uniformity compared to 18.5, thicker parts can be effectively compacted. Here is the effects of compacting. In the figure 18.7, it shows the effect of compacting pressure on green density. Separate curves are for several commercial powder. In the figure 18.8, compaction of a two thickness part with only one moving punch. In the figure A, it is the initial condition, and in the figure B, it is the after compaction by the upper punch. And lastly, in the figure 18.9, it shows the two methods of compacting a double thickness part to near uniform density. Both involve the controlled movement of two or more punches. In table 18.2, features that define the various classes of press and sinter PM parts. In class 1, level 1, the press action is single. In class 2, level 1, the press action is double. And in class 3, second level, the press action is double. And last is the fourth class, more than 2 levels, the press action is double or multiple. Classes of powder metallurgy equipment. The complexity of the part dictates the complexity of equipment. Equipment has been grouped into classes. In figure 18.10, sample geometries of the 4 basic classes of press and sinter powder metallurgy parts. Complex compacting. If an extremely complex shape is desired, the powder may be encapsulated in a flexible mold, which is then immersed in a pressurized gas or liquid. Process is known as isostatic compaction. In warm compaction, the powder is heated prior to the pressing. The amount of lubricant can be increased in the powder to reduce friction. Because particles tend to be abrasive, tool wear is a concern in powder forming. Sintering. In the sintering operation, the pressed powder compacts are heated in a controlled atmosphere to right below the melting points. There are 3 stages of sintering. The first stage is the it is cold, burnt off, or purged. It compounds any air and removes lubricants or binders that would interfere with good bonding. The second one is the high temperature. Desired solid state diffusion and bonding occurs. The third stage is the cooling period. It lowers the temperature of the products in a controlled atmosphere. All three stages must be conducted in oxygen-free condition. In Table 18.3, it shows typical sintering temperature for some common metals and materials. Hot isostatic pressing. Hot isostatic pressing, or HIP, combines powder compaction and sintering in a single operation. Gas pressure squeezing at high temperature. Heated powders may need to be protected from harmful environments. Products emerge at full density with uniform and isotropic properties, and near-net shapes are possible. There are other techniques to produce high-density PM products. High-temperature metal deformation process can be used to produce high-density PM parts. Siracon process, if heated perform, is surrounded by hot granular materials transmitting uniform pressure. Spray forming. Inert gases propel molten droplets into a mold. In Figure 18.11, while it is shown the one method of producing continuous sheet products from powdered feedstocks. Next one is metal injection molding, MIM, or powder injection molding, PIM. Ultrafine spherical shaped metal, ceramic, or carbide powders are combined with a thermoplastic or waxed. It becomes a feedstock for the injection process. The material is heated to a paste-like consistency and injected into a heated mold cavity. After cooling and injection, the binder material is removed. Most expensive step in MIM and PIM is the after cooling and injection. In MIM, in Figure 18.12, flow chart of the material injection holding process used to produce small and intricately shaped parts from metal powder is shown. In Figure 18.13, metal injection molding is ideal for producing small and complex parts. In Table 18.4, comparison of conventional metal powder metallurgy and metal injection molding is shown. Secondary operations. Most powders and metallurgy products are ready to use after the sintering process, and some products may use secondary operation to provide enhanced precision, improved properties, or special characteristics. Distortions may occur during non-uniform cooldown, so the product may be repressed, coined, or sized to improve dimensional precision. If massless metal deformation takes place in the second pressing, the operation is known as PM. Forging increases the density and adds precision. Infiltration and impregnation. It is the oil or other liquid is forced into the porous network to offer lubrication over an extended product lifetime. Metal infiltration fills in pores with other alloying elements that can improve properties. PM products can also be subjected to the conventional finishing operations. These conventional finishing operations are heated treatment, machining, and surface treatments. In Figure 18.14, it is shown the comparison of conventional forging and the forging of a powder metallurgy. Metallurgy preformed to produce a geared blank. Moving left to right, top sequence shows the sheared stock, upset section, forged blank, and exterior and interior scrap associated with conventional forging. The finished gear is generally machined from the blank with additional generation of scrap. The bottom the bottom pieces are the powder metallurgy, preformed and forged gear produced entirely without scrap by PM forging. In figure 18.15, PM forged connecting rods have been produced by the millions. Properties of PM products. The properties of PM products depended on multiple variables. First is type and size of powder. Second is the amount and the type of lubricant. Third is the pressing pressure. Fourth is the sintering temperature and time. Fifth is the finishing treatments. Mechanical properties are dependent on density. Products should be designed and materials should be also selected so that the final properties will be achieved with the anticipated final porosity. In PM materials, in table 18.5, comparison of properties of powder metallurgy materials and equivalent wrought metals are shown. And it is noted that how porosity diminishes mechanical performance. In design of powder metallurgy parts, there are basic rules for the design of powder metallurgy parts. First is the shape of the part must permit ejection from die. Second is powder should not be required to flow into small cavities. Third is the shape of the part should permit the construction of strong tooling. Fourth is the thickness of the part should be within the range of which powder metallurgy parts can be adequately compacted. And the last one is the part should be designed with as few changes in sections thickness as possible. The other basic rules of PM parts are parts can be designed to take advantage of the fact that certain forms and properties can be produced by powder metallurgy that are impossible, impractical, and uneconomical by any other method. The design should be consistent with available equipment. Consideration should be made for product tolerances. Design should consider and compensate for dimensional changes that will occur after pressing. In figure 18.17, examples of poor and good design features for powder metallurgy products. Its recommendations are based on ease of pressing, design of tooling, uniformity of properties, and ultimate performance. The next one is powder metallurgy products. Porous or permeable products such as bearings, filters, and pressure or flow regulators. Products of complex shapes that would require considerable machining when made by other processes. Products made from materials that are difficult to machine or materials with high melting points. Products where the combined properties of two or more metals are desired. Products where the powder metallurgy process produces clearly superior properties. Products where the powder metallurgy offers an economic advantage. Here are some advantages and disadvantages of powder metallurgy. The advantages of powder metallurgy is elimination of reduction of machining, high production rates, complex shapes, wide variation in compositions, wide property variations, scrap is eliminated or reduced. And the disadvantages of powder metallurgy are inferior strength properties, high tooling cost, high material cost, size and shape limitations, dimensional changes during sintering, density variations, and the lastly is the health and safety hazards. In Table 18.6, it is shown the comparison of four powder processing methods. It shows the characteristics and it shows the four powder processing method like conventional press and sinter, metal injection molding, hot isostatic pressing, and last is the powder metallurgy forging. Summary: powder metallurgy can produce products out of materials that are otherwise very difficult to manufacture. Powder metallurgy can be designed to provide the targeted properties. And lastly is the variation in product size, product rate, quantity, mechanical properties, and cost. That's all, and thank you.